Welcome to Triple S Physics. Angular momentum. The electron can revolve around the orbital. So it has a total angular momentum L and it has the spin angular momentum S. According to quantum mechanics, the angular momentum can be denoted by J. The angular momentum operator in position can be represented by the following way. So initially classical way, the angular momentum L of a particle can be written as L equivalent to r cross p. So here r is the position vector. It is represented by I cap x, j cap y, k cap z. In the same way, the momentum operator can be written as for the particular particle. So for three axes x, y, z, for the unit vectors I cap, j cap and k cap. So similarly in quantum mechanics, the operator associated with the linear momentum can be represented by P is h cross by I into del. So here 1 equivalent to minus 1. So then the momentum operator can be written as L equivalent to r cross P. So we know the momentum operator h cross by I into del. So substitute this value in this equation instead of P. So r cross h cross by I into del. So this equation can be rewritten as h cross by I into r cross del. So similarly, so this L can be represented for three axes. For example, x, y, z axis. So this angular momentum can be written as Lx, Ly and Lz for the different angular momentum operators L. So this equation 2 can be modified as, so equation 2 is L equivalent to r cross P. So where L is for three axis I cap Lx, j cap Ly and k cap Lz. So r is the position vector. So h cross by I from equation 2. So this is position vector cross, then momentum vector P, I into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z. So the left hand side we can write the same way. Then this two terms r cross p can be written in the matrix forms. Then compare the coefficients of I, j and k on either sides of components of angular momentum operator can be written as, so in the left hand side I cap Lx plus j cap Ly and k cap Lz. Then h cross by I, then we can I cap into, so we can so while we are solving the matrix, no, so similarly we can write the I cap and j cap, k cap. So for I cap, so leave these rows and columns, y into dou by dou z. So in this direction minus z into dou by dou y. Then second minus I minus j cap into, so leave this columns and row, then x into dou by dou z minus z into dou by dou x. Then third plus k cap into, so leave these rows and columns, so x into dou by dou y minus y into dou by dou x. So this is the third term. So compare I, j and k coefficients on both sides of this equation. So here first initially I terms. So here I coefficient Lx, here I coefficient h cross by I into y dou by dou z minus z dou by dou y. Then here j cap coefficient Ly equivalent to here minus, so here in front of j cap coefficient, so there is a minus symbol, so multiply with the minus symbol. So this term can be rewritten as, so minus x dou by dou z plus z dou by dou x. So h cross by I into z dou by dou x minus x dou by dou z. So then compare the k coefficient. So here k coefficient Lz in the left hand side, then right hand side h cross by I into here dou by dou y minus dou by dou x. So these are the Lx, Ly components following the commutation. So it can be satisfy the following commutation law. So Lx, Ly equivalent to IH cross Lz. So xy subsequently z, Ly, Lz can be written as IH cross Lx. Then Lz, Lx can be written as IH cross Ly, Zx, then next angular momentum y. So in the compact form or simply it can be written as L cross L equivalent to IH cross into L. So this is the angular momentum. Similarly, the spin angular momentum can be written as spin angular momentum can be denoted by the symbol S. So in the same way, Sx, Sy, the commutation relation gives the value IH cross xy after Sz. Sy, Sz equal to IH cross Yz then x. Sz, Sx equal to IH cross Zx then Sy. But S squared Sx equivalent to S squared Sy equivalent to S squared Sz. So these commutation relations give the values 0.